Alright. Can you all see the screen now? Can? Alright, everyone is back. Okay, I hope that you already make your coffee. I already have my coffee here, but it's still hot, so I'll wait for a few minutes. Okay, so now let's move to solutions. For solutions, you all know what a solution is, right? A solution is a homogeneous mixture of more than one substance in one phase. Homogeneous means one phase. Okay, so for example, you have the solute, which is the minor components of a solution, and you also have the solvent, the major component of a solution. Mostly in the lab, we are using water as our solvent, but in the future, if you work in an organic laboratory or if you deal with organic compounds, then there are so many solvents. It can be like, for example, hexane could be a solvent if you are dealing with oils as your sample, or maybe ethanol, okay, alcohol, yeah, so many, okay. But mostly if you are in an analytical lab or a general lab, just like what we're doing, then mostly we will be using water as our solvent. That's why the last time when you did the first lab on stoichiometry, remember you have your copper sulfate, magnesium chloride, and the other compounds that you handled last time, and then later on you dissolved it in water as your solvent. Okay, concentration is the amount of solute per unit volume or mass in a solution. There's so many types, okay, but for you or in class, we normally use molarity, which is the moles of solute per liter of solution. There are a few more. Next time you will come across normality, molality, so many, but for now, let's focus on molarity. Okay, next. Okay, I have the triangle again. In the lecture notes, you don't have the triangle, but for the LSP, I want to introduce to you some of the my little tips and tricks that I actually do so that I can easily remember all these formulas. Okay, so a while ago we have the green triangle, the red triangle, and then down here the blue triangle for solutions. So for here, for this one, okay, let me have the pen, the red pen. So N is for the number of moles of solute. Remember, N a while ago, it's also the same with what we did, the first two triangles. So N is always common. Then you have here the concentration and the volume. So if you're looking for N, so you just need to use the concentration times volume. That's why, remember, in M1 V1 is equal to M2 V2. We said that the number of moles in M1 V1 is equal to the number of moles in M2 V2. Okay, because mole per liter times liter, which is, for example, mole per liter for M, big M for the molarity, and volume, it's also in liter. If you cancel this one out, what is left is mole. So this is, if I, using this triangle, then C is just beside V, so you just multiply. And then if I ask you to get the concentration, then using this triangle, N is on top, V is at the bottom, so you know that you have to divide the number of moles by the volume in liter. Okay, and then if I ask you to get the volume, I give you the number of moles and the concentration, then where is that? V is here, so formula will be N divided by C. Okay? Ken? Now, let us do this question. Let's move to the whiteboard again. Let me find and copy that question first. While I'm looking for it, you can just read through and start your calculations. Okay, but here it is for the whiteboard again. Whiteboard, whiteboard. Okay. Loading. It takes a while for the whiteboard to load. Yeah, because there's so many so many things here. And the trick that I found today, I discovered, is this lasso tool, and I'm so happy with the lasso tool now. Okay, calculate the mass of oxalic acid needed to prepare 500 ml of 0.025 mole of oxalic acid solution. Then in the periodic table, hydrogen is 1, carbon is 12, oxygen is 16. Okay, it's 11:13. Let me give you, I think this one takes a bit of time, huh? The third, maybe 3 minutes first, and then maybe after 3 minutes, I'll check whether at least majority of you have answered it. If not, I'll extend it to 5 minutes. But try to solve it as fast as you can, because remember, during the quiz, you only have an hour to solve a few questions, so you have to get used to solving it as soon and as fast as you can. Okay, then write it here. 3 to 5 minutes. Okay, 3 minutes first. Then if by 3 minutes everyone is not yet haven't finished, I'll extend to 5. So as soon as you have the answer, put it here in the whiteboard. All right. I think all of you. Okay. The correct answer is 1.575 grams. Okay, I can see that some of you got the correct answer. Okay, so let me share the screen again and let's find out how to solve this problem. Okay, hold on. I'm preparing the slides. Then we can resume. Okay, good. Good. I only found out that there's an option for resume. Okay, you all know that I'm used to the BBCU and I seldom use MS Teams. So yeah. Okay, let's go back here. Calculate the mass of oxalic acid needed to prepare 500 ml of 0.025 mole per liter of oxalic acid. So down here, you are given with the molarity, you are given with the volume, and then if you use the roadmap originally from here, you already know that you can get the number of moles, and from the number of moles, you can convert that to the weight. Okay, let's see. Okay, the first thing is molarity times volume so that you can get the number of moles. And then from the number of moles, you also have the molar mass, which for example, H2 C2O4 plus 2 water. So how do we do that? Carbon, hydrogen to this is for the carbon. So 12 times 2, 12 from the periodic table, and then you have your hydrogen, and then 16 times 4 for the oxygen, and of course 2 water of hydration. You know, water is 18 times 2, so the molecular weight or molar mass is 126 gram per mole. And if you remember the triangle, then you know that the mass is equal to the number of moles multiplied by the molecular weight or the MR. Okay, so 0.0125 times 126, the MR is equal to 1.575 grams. And if you can still remember what we said a while ago about AR, MR, AR is for a specific element, okay? Then MR is just the addition. You just add up all the molecular weights. Then you have two different types, okay? The formula mass and the molar mass. Then you all know. No, I'm at page 18. Is it showing page 1 to all of you? I'm at page 18 now. Can you all see page 18?
Yes, we can.
Sorry?
Yes, we can see page 18.
Ah, okay. Thank you, Professor. Yeah, yes, can page 18. Okay. I'm confused. Okay. Grace, maybe your internet lag. Maybe you can refresh. Okay, so down here, what do we said about the MR a while ago? If it's an ionic compound, the question can ask you about the formula mass, or maybe can ask you about the molar mass. But at the end of the day, it's asking for the same thing. It's asking for the molecular weight, where you need to add all the atoms or the elements and then the number of that in a particular compound, so you get your molecular weight. Okay, so the reason why I'm putting all this together, because sometimes when a question is given to you, then you are used to say molar mass or molar mass, or let's say formula mass, then I give you atomic mass, then you find it a bit confusing already, but it's actually referring to molar mass and molecular weight or formula weight are all the same thing. Now let's move to dilution. Just a while ago, we also covered a bit about the dilution, right? Even, I think this is still fresh because this week we have our lab number 2 about titration and dilution. Okay, lab 1 is also about dilution, if I remember correctly. So down here, what volume of 12 molar HCl is required to prepare 500 ml of 2.5 molar of HCl solution? Okay, so remember before dilution, now you have a high concentration but the volume is less. But when you dilute, now what happens is that you have a higher volume but the concentration becomes lower. So at the end of the day, as I keep on mentioning to you, the number of the number of moles before and after, before dilution and after dilution remains the same. Okay, that's why you can say formula M1V1 is equal to M2V2. Now, I'll give you some time. I don't know whether you can write in here. No, you have the option to write in this whiteboard. But if you don't have, then I can just quickly, where is the whiteboard? Share the whiteboard and then I'll give you time. This is supposed to be a bit easier, so I'll give you 1 to 2 minutes to do it. Okay, here's the whiteboard. And let's go to my, I can select. How about my lasso tool? Let's go here and ask you, okay, let me copy it. The volume of 12 molar HCl is required. Okay, I won't copy the question anymore, but maybe for the benefit of the rest. Correct. The correct answer is 104 ml. Okay, did everyone got it correctly? You got it already? Okay, if you don't know how to solve that, maybe you can just raise your hands. Then I can spend some time on explaining how to do it. But if it's quite direct, then I'll just directly shift back to our presentation slides. Okay, I want to spend some time on this one because I believe this week you all are expert on M1V1 is equal to M2V2 already because we've just completed our second lab. Okay, and you all have seen it in action and how to do it. Okay, so I will go back in my slides. Okay, thank you. The correct answer is yes, 104, and I'll resume in slide 19. I'm in slide 19 now. Correct answer is 104. Okay, so 12 times V1, you don't know, that is your for the HCl. And then you need to have 2.5 molar of HCl times 500 ml is equivalent to 0.5 liters. So you just multiply the 2 and divide by the molarity divided by 12. Then you get 104 liters or 104 ml. Then now you have the Avogadro's law. Avogadro's law is the volume occupied by an ideal gas. Okay, the key word here is it should be at constant temperature and pressure. And if you meet that condition, it means that it is proportional to the number of moles of gas. Okay, so let's say I have here the volume. Okay, I also give you the formula here. Volume divided by the number of moles is equal to constant K3. Okay, so the changes in mole and volume can be calculated by rewriting this equation. So we have V1 divided by N1 is equal to final volume divided by the final number of moles. So if, for example, you have this formula, V1 divided by N1 is equal to Vf divided by Nf. So if you have 5.5 mole of carbon monoxide and it occupies 20.6 liter, how many liters will 16.5 mole of carbon monoxide occupy? Okay, it's the keyword here, same temperature and pressure. And you know that for Avogadro's law, you need constant temperature and pressure. Okay, so maybe instead of us using the whiteboard to save some time, maybe I need your help to write it down here in the chat. I'll give you a minute to do this. Okay, formula is, what's the formula again? V1 divided by N1 is equal to the final volume divided by the final number of moles. Okay, and the correct answer is how much? Yes, the correct answer is, let me see, 61. Yes, it's 61.8 liters. Okay, how? Let me see. Okay, I'm glad that you all managed to solve that. How do we do it? Okay, so as I told you, if you remember the formula, it will be easy, right? And I also told you, whatever that the question give you, these are just right there to, I don't know, to me, it makes it a bit, to make it sound complex, but it's really easy. Okay, so if 5.5 ml of carbon monoxide occupy 20.6, how many liters will 16.5 of carbon monoxide occupy at the same temperature and pressure? So 20.6 divided by 5.5, then the beginning, V1 is missing and 1 is given. So you just 16.5 times 20.6 divided by 5.5, then all of you will get 61.8. Okay, very good. This is another important formula or another important constant that you must remember. Molar volume. Remember, we have molar mass a while ago and now we have molar volume. Okay, and then you will say, hey, Miss Cathy, how come all the names are like almost the same? I don't know why, but it looks to me that chemists and scientists are not so creative in giving names. Okay, so molar volume, molar mass, formula mass, molecular mass, molecular weight, it all, okay, it will sound confusing if you don't know how to recognize or identify them. But what is a molar volume? It is the volume occupied by 1 mole of any gas. Okay, but just like the Avogadro's law a while ago, it should be at a while ago, you remember, it says here that it should be constant temperature and constant pressure. But for molar volume, it should be at STP. So you have the standard temperature and pressure. So standard temperature is at 0 degrees Celsius or 273 Kelvin. And for pressure, it should be at 1 atmosphere. So if these conditions are met, if I tell you 1 mole of gas, how much volume will it occupy? Then you know that it is 24.4 liters. So there might be questions that will ask you how much is whatsoever at STP. So even if they don't give you the volume, you know already that the volume is equivalent to 22.4 liter, and that is a constant. Okay, so the formula would become volume of gas at STP divided by volume of 1 mole of gas at STP. Then you have the number of moles. So N is equal to V over 22.4. Okay, so let's say I tell you I have 44.8. That's the volume of the gas at STP. Then I ask you to calculate the number of moles. Then if it's 44.8 divided by 22.4, then what you will get is just 2. That's the number of moles. Number of moles will be 2. Okay, so I like this one because you have the constant there, so I just directly divide and I get the answer already. Okay, so this one, I ask you, okay, I already showed you how to do it. Calculate the mass of oxygen gas at STP if, for example, you have 48 liters of oxygen, and I've given you oxygen, like 16 from the periodic table. So some of the questions will give you all this. For example, I will give you a molecular weight. Then you will think, do I need that or not? And probably you need, right? Because you're asking, this one is asking you for the mass. And we know that from that STP, you can only calculate the number of moles. So from the number of moles, you have to convert it to the weight. So how much would that be? Maybe you can help me to write it here in the chat window. Okay, instead of asking you to do on the whiteboard for the interest of time, maybe you can just write it here in the chat window so we can save some time from shifting to the from the presentation slide going to the whiteboard. Of course, I like the whiteboard, but okay, I think we can save some time by directly writing it here. And don't worry, whether you got the questions, your answers are right or wrong. Here, we don't judge. We're here to learn from one another. Okay, so just whatever it is that you've calculated, just put it there. Okay. How much is the answer? What do you think? Okay. Yes. The correct answer is 68 point. Is it 68? Is it 68 point something? Yes, it's 68.5. So how did we get that? How to do, okay. I press this navigate forward. Okay, so the molar mass, okay, so 48 divided by 22.4, then you'll get 2.14. Then you multiply it by the AR, 16 times 2, then you get 32. So mass of your oxygen, sorry, excuse me, will be 2.14 times 32, that is 68.5. 5. Okay. Is it clear? Can we move to the next one? Now we are at the chemical equilibrium. Okay, chemical. I think some of the students, when I send the feedback form, then you all said that this is an area that you would like to revise. Okay, so I included it here in our revision. First, okay, equilibrium, that is a state when that you reach, or the chemical reaction reached by because of the reversible reaction. So when forward and reverse reaction rates are equal. Okay, it is represented in the chemical equation with the double arrow instead of the normal single arrow that we use in most of the equations. So whenever you see the double arrow, it means it's reversible. The reaction can go forward and backwards. Unlike the other one, it's always forward to produce your products. But depending on the conditions, if you have a reversible reaction, instead of moving forward, it can go backward. So chemical equilibrium is said to be dynamic. Okay, it's moving because reactions and products are continually being formed and reformed. Okay, so in that you also have an equilibrium constant. Okay, it is the measure of the relative amount of reactants and products in a reaction system at, okay, the keyword is at equilibrium. Okay, so let's just say you are given A plus BB, so lowercase a as the coefficient of A, compound A, plus lowercase b as the coefficient of compound B is equal to lowercase p as the coefficient of compound P, and lowercase q as the coefficient of compound Q. Okay, so this is where what I'm telling you a while ago. To get your K equilibrium, then it's so easy. You just have to, okay, let me erase this. The main formula is, let me use this one, products over reactants. Okay, so let's say I have here P. So P raised to its coefficient small p, and then multiply by concentration of Q raised to its coefficient mini q, or small letter q, lowercase q, divided by, as I said, products over reactants. So we start on the right side before, and then we divide it by the left side. So A raised to A multiplied by the concentration of B raised to B. Okay, so this is a general formula. Okay, so you don't have to be confused with that. No matter how complex, you just look on the balance equation, and then remember products over reactants, and then you raise it with the coefficient. So solubility product constant, I'm not so sure whether I've given this, so we've covered this. I think, no, I won't, yeah. But it's basically the same with the previous one. It's just that when you have a solubility product constant, you only focus on the product side. Reactant side, no need. Solubility, only the products here. No need to divide by whatsoever. So I won't give you this type of questions. I've seen that our syllabus don't cover this, so maybe I'll just skip this and go back here. So you have here a closed system initially contains 1 times 10 to the minus 3 molar of hydrogen, okay, and then 2 times 10 to the minus 3 molar of iodine. So from there, if you have the ice table, I normally call this ice table. I, C, and E. If you write this ice table, first thing that you have to do is to write down the concentrations that are given to you in the correct spot in the table. Okay, so initially, it will always tell you initially or at equilibrium. So initially, then you write down 1, 2, so minus 3, and then 0. At 448 degrees Celsius, the reaction is allowed to reach equilibrium. Analysis of the equilibrium mixture shows that the concentration of HI, okay, is 1.87 times 10 to the minus 3 at equilibrium. So in my ice table, then 1.87 times 10 to the minus 3. So if my total here is 0 plus this 1.87 times 10 to the minus 3 is 1.87 times 10 to the minus 3, then what it means that what is missing here is the positive 1.87 times 10 to the minus 3. Correct? And then I can just, from my balance equation, I have 2 moles of HI and I have H2 and I2 at 1, 1. So I can just divide this value by 2. So I have 9.35 times 10 to the minus 4 and then 9.35 times 10 to the minus 4. Since this one is positive, my output is positive. For me to produce this, of course, just like a container or a cookie, just like a cookie jar. Okay, if for example, you have 2 cookie jars or 3 cookie jars, and then in my cookie jar, I already took from this jar and this jar. Maybe I took 9 cookies here and 9 cookies here. Then in my third jar, I have a total of 9 plus 9, 18 cookies already. So that is positive, minus of, minus of. So that's why you have the negative sign here. And then if you add it together, sorry, excuse me, 1 times 10 to the minus 3 plus negative 9.35. Sorry, let me drink water first. Minus 1 times 10 to the minus 3, excuse me, and then plus negative 9.35 times 10 to the minus 4. Then what you'll get is the 6.5 times 10 to the minus 5. And you directly do this, you can get 1 times 1.065 times 10 to the minus 3. And you know your KEQ is equal to products over reactants. Then you just substitute all this. 1.82, 1.87 times 10 to the minus 3. You got 2 there, so that is your raised to the 2. And then here, it's to both 1, 1. So you just directly multiply the concentrations that you get at equilibrium. Then you get your KEQ at 50.5. Okay. Now let's move to the Le Chatelier's principle. So when a system at dynamic equilibrium, remember equilibrium is, we said it's dynamic, it keeps on moving, you are producing your products and reactants at the same time, it goes back and forth. Okay, the system will adjust itself to minimize the effect of the perturbation or any stress that you give into equilibrium reaction. So let's say I have a concentration. If I add reactants to, for example, I add here, I increase this one. From a system at equilibrium, it will drive the reaction forward. Okay? Because you just imagine you have added too much here, and let's just say I have a container, 2 container, right? This container at equilibrium can only hold this much. So if you add more of this, what will happen is that this amount will not stay there. Instead, it will move forward so that it can fill this vessel until it both is at the brim. Okay? So if I, for example, remove here, let me erase this one. If I remove this one, so this one, hydrogen becomes lower, then what will happen is that instead of going forward, this one will move backwards, reverse, because just like in our given example here, the other one, this one, you increase it. So instead, you cannot fill this one up. It should move to the other side. So that's what's basically is happening here, okay, in concentration. Just think of that two containers. So if you increase in your reactants, then it will shift forward. If you increase or decrease your reactant, the reaction will shift backwards. Okay? So if now if I said I'll increase this one, then where will the reaction go? Then it would go reverse. Right? Okay, then if I lower this one down, this one is low, then what will happen? This should move forward. So think of that two containers. Then you will not be confused about forward, backward for the Chatelier's principle. Then what happens if it's a temperature? Increasing temperature will drive the reaction in the direction that is endothermic. You know why? Because you just remember, for example, I have N2 plus 3H2 plus 2NH3. If I increase my temperature in the reaction after the reaction, it is like I am putting heat here. So if I increase this, what will happen? It should move forward, right? And decreasing the temperature will drive the reaction in the direction of exothermic. So it is like saying I added heat at this site. Because remember, when the reaction is exothermic, what happens? The environment becomes hot because your reaction releases energy or heat to your environment. If it's endothermic, what happens is that it accepts the heat or it becomes colder. The system becomes colder. Okay? So next, the Chatelier's principle, what happens if you have pressure and catalyst? Maybe we can end it here because I still have a few slides here. But for the pressure, if I increase the pressure, this is very important. What's the difference? In pressure, you have to look on the fewer number of moles. Increasing pressure will drive the equilibrium toward the side of the reaction that has fewer moles. When you decrease pressure, it will drive the equilibrium towards the side of the reaction that has more moles. So let's say, so this is like, I normally would draw this as like something like this. So that I will remember it. When I increase the pressure, then this one goes down. And what will happen is that I will look for where there is less number of moles. I have 2 here, I have 1 plus 3, then I have a total of 4. So if I increase the pressure, reaction will go here at the product side because I have less number of moles. But if, for example, let me draw again our nice arrow. That's how I remember it. Then we said decreasing, so it becomes so if it's low, it will go to where it is high. I have 2, I have 3 plus 1, there's 4. Then it will go to this side. So reaction will be reversed. Then a catalyst, it's just there to speed up the reaction. So it reduces the time needed for the reaction to proceed. but they don't do anything. So they do not affect the composition of equilibrium. So let's just say I have this and I added a catalyst here. Let's say catalyst. Okay, I have added the catalyst there. It will not move here or here. No, it will still be the same. But let's say this reaction takes 3 hours. If I put a catalyst, then it can be completed by, let's say, 0.5 hours. It does not do anything except to speed up the reaction. Okay, so down here we got the Bronsted-Lowry acids and bases, and I know that in the slides you can be confused of what's the difference between Arrhenius, Lewis, and Bronsted-Lowry. Okay, they actually mean the same thing, but they are looking. We have this lingo here where we say same but different, right? So it's actually the same, but they represented it in a different way. Like for example, acid is a compound that produces hydronium ion in water, while a base you produce hydroxide ion, according to Arrhenius. And then to Lewis, he said electron pair acceptor. So he focuses on the electrons, and a base is an electron pair donor. But for Bronsted-Lowry, you see, they look on the opposite. Electron here, proton here. So if it's an electron that accepts, opposite with that would be a proton that donates, right? So it's the same thing. Then for bases, electron pair donor, if you look on the opposite for Bronsted-Lowry, because they are looking at the proton, then if this one donates, it should accept if it's a donor. If it's electron donor, proton acceptor. So this is a summary of that. I hope that that will help you. And I have a few here for acids and bases. Maybe we can cover this next time because there are so many things there. And we still have thermochemistry and what else? Thermochemistry and electrochemistry. But for now, I need your help to help me to accomplish this form. Okay, hold on na. Okay, help me to accomplish this form. And okay, give me a raise of hands. Would you like me to upload the notes? Yes or no? Yes, if you want. If you don't raise your hands, then I won't. Okay, but probably, okay, I'm seeing 2, 3, 4. I hope that the notes can help you because I put everything together as a summary and it's easier for you to compare. I can see 2, 4, 6. We got 12. Okay, 50-50. How about the rest? Do you want the notes? Don't want? Also can. How many? 2, 4, 6, 7. Okay, 7, 2, 4, 6, 8 over. Yeah, okay, I got 8 over 12. Okay, so I'll upload it in the same channel in this MS Teams. Okay, so you can find it there, and maybe from time to time I'll try to update it in preparation for the next one, or maybe I'll just complete this full slide for the first 2 topics, and let's see whether I'll put the other 2 here also. Maybe I'll just update this one so that you can also just look at one full slide, then no need to have so many files. Okay, Ken, have you submitted the form already? I hope that you learned something today. Okay, please submit the forms. I'm seeing 4 of you have submitted already. How about the rest? Okay, next time, I hope that I can spend more time in doing this revision and also I would want to also spend some time to give you a set of questions so that you can solve it. But I feel you need all the theories to be put together. I'm not so sure whether you like the uh, this concept that I did. So I give you the summaries and all this, and then we solve problems, or you want it to be more like tutorial type. You solve the problem first and then we discuss, or something like this. Maybe you can put it in the, okay, maybe you choose a tutorial. It will be more on hands-on, or same as today, or today, like today, like today. Okay, so today we did a mix of both. So I give you a summary of some of the lessons, like my little tips and tricks, and then I ask you to solve some problems. Or it can be you want it more hands-on, because I want to listen to what you want. If you want it more hands-on, like what we normally do for the tutorial, then I can prepare questions and then give you some time to solve it, and then let's discuss. Okay, it's 12 o'clock. It's lunchtime. I hope that you all go and enjoy your lunch. Have a nice day, and I'll be recording this session. So I've actually recorded it so you can have access to that. And for your classmates who cannot make it today, you can tell them that I've recorded the session so they can just watch it. And also next week at the same time, let's continue with the rest of the topics. As you've mentioned, you want something like the one that we did today, so I'll continue with that. Remember to be a blessing to others, and I hope that you learned something from me today. Bye everyone. Enjoy the rest of the day. Okay. Okay, so I'll release that one. Answers for electrochemistry. Okay, good that you asked me. Tutorial question for electrochemistry. Okay, just now. Okay, it's already available. Thanks. And then probably for the lab also, I'll release the solution for acids and bases later, because I still have to upload that. Okay, anymore? Anything, you just let me know. We don't have ICQ next week. You all can focus on the lab, and then focus on revising for your MDMP. I know that you have an online quiz on MDMP. Okay, for term test week, ICQ. Okay, no ICQ for term test week. No, I've decided not to go and have ICQ and online quiz at the same time, so that you all can focus on the online quiz. Okay? Don't worry. Yeah, we can schedule organic chemistry on another day. Just focus on the online quiz first. Any more questions? No more questions. I can stop the recording here.